Bom dia a todos. Vamos dar início aqui ao segundo dia do nosso 14º Encontro Unificado de Computação do Piauí e ao nosso 11º Simpósio de Sistemas de Informação. Vamos iniciar o segundo dia do evento com a palestra do nosso querido amigo professor Alfredo Núñez, intitulada Elements of Intelligent Railway Infrastructures. O professor Alfredo vai fazer a sua explanação e a gente espera contar com a interação de todos pelo nosso chat, perfeito? Bem como convido todos a se inscreverem em nosso canal. Hello, my friend Alfredo. Thanks for accepting our invite. You can present your lecture. So, good luck. Thanks again.
Ok, so, muito obrigado, Ricardo, Débora e Romuere, por la convite. Tremendo placer estar aquí hoy. I'm Alfredo Núñez, and yeah, I'll be presenting my research work about intelligent railway infrastructure. So right now, here I am. So I'm an associate professor at the Delft University of Technology in the Netherlands, and I work in the section of railway engineering. My research is about intelligent railway infrastructure. So what I'm intended to do is to actually create the sort of digital brains, because the infrastructure is inanimate. It's not a biological system, but it has a lot of behaviors that resemble living beings, actually. So in my research, I'm trying to incorporate the intelligent elements in the infrastructure so that it can perform much better over time. It can then, be more available with less failures or so. And then, it provides to provide a nicer, better service to public. Actually, the motivation for working on this field, one of the first comments I got when starting at railway engineering, was that the rails, the components you see over here, I was told that they behave like an elephant, in the sense that they could remember over years and years whenever they had a defect or a problem. Didn't matter how much maintenance was performed there, the problem always reappear again and again. So then the colleagues thought, oh, this is like an elephant, always remembering. Now we know that the problem is there because of some other situations, so other physical conditions. Yet, there's some resemble over there. The railway also has other sort of defects, and actually, the infrastructure sometimes tries to talk to us. And here I'm going to click an audio from where you will hear first infrastructure affected by this type of defect. This is called corrugation, and it's in a very high pitch noise that you will hear. And the audio after will be about a hanging sleeper. So whenever the trains are passing by those locations that are affected by the performance, let's say that the performance is not the best, then the railways try to talk to us. So that's the first type of defect. And that's the typical noise of a hanging sleeper. So somehow inanimate, but still trying to communicate with us, that it needs some maintenance. This field of research is inherently multidisciplinary. That means that we don't only use the knowledge specific from the railway engineering itself, but we also make use of knowledge, information coming from engineering structures. Particularly for the intelligent aspects, we also make use of artificial intelligence, systems and control, and many other fields. So for today, I divide my presentation in two parts. The first one is about a brief introduction on railway asset management, so you can understand on the challenges that we are facing for the optimal management of railways. And then later I'll be discussing some few elements on problems and cases that can be tackled by intelligent systems. So here, yeah, it's a nice video from the Netherlands, a very beautiful country. We have here the passenger train going through the bridge. You can see also over here the windmills. So I wanted to share this with you. The motivation for managing the infrastructure has to do with the aging of it. Railways, but also roads and so many other infrastructures, they are facing a continuous aging, also due to the usage, also due to the weather conditions. And this is the management of this is a challenging problem worldwide. There are bridges that are so old that they need full replacement. And such a type of project is very difficult, very costly to do. And when you're facing the same problem everywhere, you really have to optimize where's the most efficient, the most the best location to start doing that. And then, yeah, we need information, we need data, we need knowledge for such a type of decision. In the Netherlands as well, we have another challenge, and it's that we are in one of the most dense and intensely used railways. That is that basically we want to have availability of our railways 24/7. Additionally, the infrastructure sector and railways cannot only help with fulfilling the green agreements, because railways is one of the most sustainable transportation means, but it can also, by analyzing and providing new elements of infrastructure, it can also help the boost of digitalization. And green technologies, digitalizations, are going to be the core of the future economies, or the actual economies of today. So actually then working on this research field is very interesting, and that's why we aim for accelerating developments here. In the table you see over here, we have some examples of defects, of failures. You see sometimes the defective train, signal failures, switch failures. Those are infrastructure related problems that with technology, some of them could have been prevented. There are also other sort of situations, collisions with persons on the track. They are also related to security. There could also be actions that could be done in the safety systems. Yet for those other problems, we indicate that they are not fully, let's say, due to the infrastructure itself. So we have here third parties basically involved. We have also problems, for instance, with the energy system, catenary failures. And although the number of those failures is lower than the defective trains, when we get a catenary that is falling because of strong winds or for other conditions, we have that the whole railway line is not available anymore. While when we have one defective train, if you put the train in the right location, you have only a piece of the track that is unavailable. So then here you see also the effects of duration, different problems, different frequencies, different effects. So all of this has to get into consideration when deciding on the sort of technologies, the needs that you have, and actually the how much you can expect out of the new developments, new technologies for solving such a type of problems. Over here we see two things. There are opposite objectives in general. One is the performance, the other is the cost. If we want a better performance, there will be more cost involved. And I believe that all the infrastructure managers, the railway infrastructure managers in the world, they want to perform in a way that they can provide services free of risks, that they can also provide the social benefits in society to contribute, for instance, to the reduction of CO2. But the complexity of the infra managers is different. We have the regional railways that usually they don't have much support, not much budget to work with. So basically they can take care of some type of failures, executing tasks, yet it's not possible for them to think forward in the future in the sense of long-term plans, because they have to survive with the budget they have for this year. So you will see that then all of the infra managers are aiming sort of, let's say, more or less the same, yet the availability of budget is different. So here we have the first type, let's say, where they're aiming for a higher return immediately, typically rural systems. But then we also have the more elaborated, let's say, infra managers that they are meeting also not just transportation itself, but also tackling different challenges such as CO2 reduction and minimizing societal impact of the infrastructure. And during my presentation, I will show you some examples on monitoring system and maintenance. And there are two key aspects in the optimal management of the infrastructure. No matter the performance or the cost that you're aiming to minimize, both of them are going to be the tools that we will have to know what's going on with the infrastructure and to also assess what's the best thing that we can do to get it better. And we do that by maintenance. So the infrastructure, the railway infrastructure has a life cycle, also like living beings. This life cycle goes from the moment where the infrastructure is an idea. So it's in the brain of someone. So it's electrical pulses somewhere in the brain where you are already thinking of, okay, this is the type of infrastructure that we need. Then once you have the plan, you get your project done, you can have a stage of commissioning. That's when you start installing, let's say, the ballast, the rails, the components. So, and after this, we have the moment of operation. After years of operation, some components they have to get disposed to see, okay, how much we can recycle. And then we get again a new loop where we have to acquire new systems, or we also have to maintain some other systems, and then we get this whole life cycle over and over again. So although the infrastructure, if you look at it one day, and it will seem to be the same, but when you look at different years, different months, you can notice the differences. So this life cycle, in the case of infrastructure, is rather long. We're talking about 20 to 40 years for railway tracks. They have a slow dynamics, like the one of degradation, but there are also fast dynamics, and this makes things complicated, because once you have a problem with a switch that is imminent, that is about to happen, it will occur in few hours. It will occur within one day. So if you are aiming for monitoring plans in the long term, then okay, you can find certain problems, but not this one. So then actually you need then to combine the time scales of the monitoring systems. The infrastructure also has a memory. It will remember the way you treat them. It will remember the maintenance plans that you apply to them. Then in general, we know from the experiences of various countries, whenever aiming for short-term savings, because budget is not always available, when we reduce monitoring, renewal or maintenance operations, we really damage the life cycle of the infrastructure. We tend to reduce it. So at the end, we have to keep operating the infrastructure, we have to pay even more costs. So this is the view of the life cycle, that actually decisions of today will have an effect, maybe not right now, but in few years more. And then the cost will be even higher. So you have to be very careful here on the way you manage things. So now, how can we then match, let's say, for instance, what's going on in the railways and the decisions that we have to do? We see in the railway field that we have about, this is one classification. To know what's going on, we have fixed sensors, fixed monitoring solutions, so at one location. We also have onboard vehicles, so that they, while on the run, they measure the condition of the tracks over longer distances. We also have crowd-based data. So for fixed locations, usually we prioritize on components that are safety critical, such as switches and crossings. So those are sensors installed at certain places of the railway. And for instance, over here, you see an example. We have here 3 different types of train. We have here accelerometers. Whenever the wheels are passing nearby the accelerometer, we get vibrations. By analyzing frequency content and comparing the signals, we can then assess if we have, for instance, wheels that are failing. And we can also know if the switch itself, in this case was a measurement in a switch, or the location itself is suffering some drastic changes over time that will indicate that that specific location requires maintenance. So then a master student did the thesis on deep learning for this sort of data, and indeed, with the railway data and the latest convolutional neural networks, for instance, you can get a classification of the type of rolling stock passing by that is rather high, above 0.9, which then is very interesting to plug into decision-making support tools. Here we have then example of onboard vehicles. So this is the one that the colleagues in China are using. And we have here multiple cameras, different angles, and then they can monitor the rails, they can monitor also the catenary system. And over here we have our measurement train, the one we use in the Netherlands for measurements. And then the same, so while the train is going on, doesn't matter the speed, 200 kilometers per hour, or 140 in the Netherlands. We collect information as we pass by the locations, and then we can detect failures, problems, or imminent situations. So then this has a larger coverage. We can cover the whole infrastructure with this type of measurements. While for the fixed locations, it's only at one place. But then, in the Netherlands, we have more than 70,000 kilometers of track. Then, we need efficient methods, and that's why then we work with the onboard measurements. Also, recently, it's getting every time more and more popular, the crowd data source. So with mobile phones, the passengers can also right now monitor their comfort. And then, for instance, we measured these colleagues from Romania, the comfort in our regional line. And then we could see that, the locations where there's more uncomfort for passengers are here and there. So that information can then go to the infra manager. Also, with the mobile phones, they provide a very strong tool actually to communicate directly with the passengers. So then if if they're annoyed or if there are other situations that could be fixed online. I think the tools are not yet fully explored so far, but we can certainly very much improve the travel, let's say, conditions, the happiness of the people by communicating directly with them whenever there are changes in the platforms or whenever there's some information they gotta do. So then you can see easily here that we have such a variety of informations and sources, and they're all relevant. And the thing is, how can we make use of them? And this is where the intelligent methods play a very important role. Additionally, let me see. So over here, this is a test that we conducted in a ring in Romania. So we measure the very, let's say, small defects like you see over here. So those are few centimeters, and with the technology we have, as the train is passing by this location at 80 kilometers per hour, we see a strong difference already in the time domain. So we have the sensors that are very sensitive to very little defects. While then when we go at a higher speed, it's even more evident that there's a problem. So actually then the technology we are developing, it's aimed for a higher speed. The higher, the better. And over here you see that, there are some issues here with alignment, some issues with a little bolt. So the problems in railways are also different at different scales. The alignment is a problem that happens over a larger region, while if you get a missing bolt, it's really like a very specific location. So we also have to deal with this issue that inherently railways is a large-scale system. Here there are also other examples. The monitoring here of with the new solutions. The sensors technology nowadays are very available. So there are could be problems with also bridges. There are also problems here with the concrete elements. So we have different sources of situations that could happen. Over here, this is the catenary support system, and it has a small different components that with the vision technology, we can first detect the places that are important, and after we can also assess if there's a particular problem at a specific location. This provides a very strong tool for the inframanagers, because then they don't have to then send people to be checking all of the components, but directly to the one that needs the specific action. So, and then here we can go for very large, let's say, the changes, till very little ones at the level of pin, or even here at the level of the isolation cables that we see over here in the isoelectric line. So finally, then we get measurements, but for what? The thing is that we can know what's going on in infrastructure, but if we do nothing about it, then things won't get better. We gotta close the loop here. And when we get the right information, we gotta match it with the respective maintenance plan. And this is what this graph is trying to do. So showing you that there are measurements, there are estimations of failures, and with the knowledge of the railway field, together with the optimization-based approaches, then you can really then have a full control of what's happening with your infrastructure. But just knowing what's going on then won't solve the problems. You really got to get your plans to actually prevent the problem to happen or to improve the condition of the infrastructure. Over here we see that in terms of decision making, there's reactive maintenance, for instance, where you wait till a problem happens and then after you fix it. The problem here is the performance is rather low, because then the infrastructure won't be available for a while. But then there are new techniques that allows you to predict when the problems are going to happen. So they require more knowledge, more technology, more intelligent systems. Yet the performance that you expect from them is much higher. So then we can then increase the complexity of the decision making, and we get every time better and better performance. So when we incorporate all technologies, 5G, Internet of Things, then we can aim for a full communication of all what's happening. With even later in the future, we might have robots that they do the maintenance by themselves. Then they will optimize and they will do all the activities in the best moment that they evaluate. So, that was the introduction to the challenges of railways. Here I would like to share with you the one day at the Dutch infrastructure, all those boxes you see are trains going from one location to the other. So this is the Netherlands, and well, it's about 300 kilometers by 200 kilometers, and this railway network is very densely used. So you can imagine that if we get the problem here or here, doesn't matter where, we will be affecting a lot of people. And the Dutch people are known for complaining a lot. So we don't like that. Of course, we like that they communicate their anger, but then we want to avoid that to happen. And this is then one of the reasons why we also develop technology that can be mounted on board. Then we don't need to stop the railway operations to get the information we need. And here you can see our measurement train. So this is a platform that we have at TU Delft, where we develop new technologies, new sensors. We mount them in our train, and then they go through the whole country, and then they collect information. So you can see also here some nice maps of the Netherlands. It's such a beautiful country, and yeah, then this also the needs of our country is also what triggers the research that we're doing. I believe that then if we were in another country where the railways is not, let's say, so intensely used, probably then the needs also might be also different. So as for the elements of railway infrastructures, then I divide the challenges into three aspects. One is perception, the other challenge decision, and the third one is about learning. So yeah, we want to treat railways as a living being. And one of the characteristics of living beings is that we can perceive how we feel, we can perceive our environment. So for railways to do that, we need to mount, we need to address the right sensing technologies and evaluation also to fully match what's happening right now with the actual situation. So we match signals with actual problems. And then we aim for a railway that can automatically decide how it is doing. What's my condition? The second challenge about decision is that once the railway is not feeling well, then it should take a pill, it should get some medicine, and that medicine is a maintenance. So that then also the railways not only knows where the problems are, but also what to do to fix them. And then this is the part where we get some decision-making optimization approaches that can be implemented in this system. So then you give the decision power to the infrastructure to suggest, to decide what it needs to get better. And finally, the learning challenge. We see that when implementing maintenance plans, there are times where some pieces of the railways could not be monitored or maintained, and then the problem repeats every year. So we really need to learn not only of the good experiences, not only of the things we're doing great, but also maybe from mistakes from the past. Then we have in the intelligent systems, we have methodologies that will help us to do this learning process systematically. So because it's okay to do some mistakes. The thing is that it's not okay is if you don't learn from them. And the technologies, the new developments that we have, they allowed actually this systematic learning from previous experiences, the good, but also the bad ones. So here I would like to share with you some examples. We've been working on this field since 2013. This is already a very old-fashioned infrastructure. I mean, old-fashioned method. The convolutional neural network is we tried many years ago with images from defects plus vibration signals from the same defect. And then we could, by neural networks, analyze what type of problems we are facing. Sometimes the images they gave us the impression that there's a severe, very complicated defect, but when analyzing the vibration signals, then we see the opposite. That is that because we really need to know what can be done with each technology. So sometimes then the best is to merge different information. And for instance, here we get locations that are changing over time. So here you see the evolution after months of measurements. And this provides us information about how fast the problems are growing. So it's the plot that you see here on top. With this information, then we can predict when is the best moment to repair all those local defects. So here we get with this very simple structure for neural networks, we see here some defects that were not detected. I believe with the new technologies, that the newest networks available in the literature, then those locations they will be learned. So it's a matter of the structure that we were using. There were also other defects here detected, and by surprise, then we get also sometimes defects that we didn't train the network to learn, but somehow it got the results. So that's interesting from neural networks, that sometimes they have this generalization capability. Then in this field, we have problems with big data. So for instance, the measurement system is of about 25 kilohertz, and that's a huge amount of information, terabytes per day. Yeah? So we have issues with the volume of the data, but also how fast we need the data to be processed, variety of the data. We need images, we need vibration signals, we need laser, we need eddy current. And all the V's of big data, they play a role also in the railway system. And here you see a way to classify big data problems. Sometimes it's not the problem of the volume, but the variety of the data. That's the most, I think, one of the most difficult challenges to overcome when providing these sort of solutions. Over here, you see an example of a project we did at, this is Rotterdam City, and we get here information of tram failure events. So by accumulating then the events, this resembles what we knew already, that during October, November, because of autumn, we get a lot of leaves from the trees falling, and the number of wheels sliding increases. Also, we get in January somehow also some events. So this sort of mapping help us to see clusters of locations that are places that this sort of problem is more recurrent. Then because the same trams are going everywhere, we believe that then those locations are with more problems because of situations at the infrastructure itself. This sort of information then provides the inframanager decisions of locations that are more interesting to analyze. Also, when measuring tram infrastructure, because we are in the city, we get also quite noisy levels of positioning. So then we have to deal with a lot of stochasticities, not just from the positioning, but also the measurement itself. And then there are techniques from intelligent systems that can help us into clustering different locations, so that then after we can analyze what's really happening there. So we combine intelligent systems with the actual railway engineering. So yeah, and each method, they will have different characteristics. You have to really play with the different options and to validate them with the actual data and the actual information of the field. There's the match between data and the field is very important for us. Here you can see, then later I will share the presentation. You can see also some other examples of information, also to see methods for clustering, for instance. The second challenge about decision indicates not only what to do, but also when to do it. Is it that the problem can wait for 1 year or so? So that's very important for the maintenance decision. It's a large scale, it's stochastic, it's a complex infrastructure. Do we need more or less sensors? Can we change the design to be able to tackle future challenges? So in places where we have a high risk of flooding or in very dry conditions, or in mountainous regions, how can we include the design to be future-proof? This is at the decision level. So over here, then we did this project then in the railways in Transylvania, and by mounting sensors in this passenger train that was in operation, we could detect the locations that had the most risk of problems regarding the rail and the track. So we shared that information with InfraManager. They knew of the top 100, about 30 of the locations. The others were new to them, but when they verify each of them, they could see, okay, when the train is passing by here, this sleeper is hanging. They could see each of the problems. So new technology will really help infrastructure managers. And then once you know all the problems you have, you really have to prioritize. So, and then this is something we do with the multi-objective optimization, with evolutionary computation, and then we can deal here with the non-convex problems, stochastic problems, large-scale systems, and information sometimes that is missing, or that you don't have enough data, or that you have a lot. Finally, the third challenge about learning, we're implementing techniques that allows the detection of components. So we know where where each component is, but then also to assess if there are defects. And then we have tried before some simple techniques. Nowadays, with new technology, we also have 3D information, 3D data, for which you need also the neural networks that are the state of the art, that can handle this sort of more irregular set of data information. Over here, we see then one example where we had already a neural network, deep learning, very good, that could detect the position of interesting places. Yet the perfect location was later always managed manually, that we have to move it a bit and to crop the right data. So what we did was that after applying deep learning, that it provides an excellent solution for most of the locations, we include a reinforcement learning approach. And here we taught this neural network to decide whether to move this box up or down or left or right, or expand it or contract it. And then over here, then you see that provided this initial condition, then this reinforcement learning approach managed to get the full information of the component that we want to analyze. And basically then once we get the location, we know the type of ball we want to analyze, we can plug in additional solutions for assessing, for instance, how loose is this bolt. Or we can then assess also other sort of problems. Finally, then in the railway systems, also in most of the industry of nowadays, the digital twins are very common. I would say that they are implemented almost in all the relevant infrastructures, because they provide a tool where you can see the infrastructure itself, and by clicking here and there, you can get the actual information of the conditions, the latest measurements conducted to those locations. So this is a technology where you combine the visualization aspects, but also once you manage to create those digital twins, you can feed them with information when there's not enough data about a failure. You can then digitally create those failure events, digitally train neural networks, and then after you can apply them and to test them in the real life. So this digital infrastructure then is a very powerful tool, and it's going to be the research focus in the coming years, definitely. So finally, then here are some challenges in general for the intelligent systems. It's always the trade-off you have to get between false positive, false negative. You gotta know the behavior of the system that you have. So don't rely only on the data. Be sure to incorporate the knowledge of the physical system. Then we get challenged with the large data volumes, also when there's not enough data. And then we gotta be very careful here on teaching the algorithms with the right information. Otherwise, you know the saying, garbage in, garbage out. So we also have then new neural network structures, and they are every time more complex. They capture more features. So this is a very dynamic field of research. I recently saw last month like 3 new structures for neural networks for rail defects. So it's a field that is evolving very fast. We are also the coming year aiming for what's called physics-based neural networks, in a way to include, when there's not enough information, the knowledge about the physical system in the learning mechanism. Also, the fuzzy logic helps so much when we have to systematize decision support tools and to support on the interpretability of the results, because once you get results, you gotta make use that the railway people can understand it. Then finally, those new neural networks are very complex, and the training of them is a non-convex problem. We tend to use the back propagation for the most simplest structure, thanks to Paul Werbus for that. But then for the latest structures, we really need to do much more about it to train them much better. And I think evolutionary computation then has a strong say to say about it. Here just a way then that in the field is being used for benchmarking new solutions on neural networks. This is the handwriting problem. Probably you are familiar with it. This is well, I did this slide, I think, like 1 or 2 years ago. So maybe there's new latest neural networks for this, but you can see here examples that the latest deep learning approach did not manage to classify correctly. But to be honest, I would also not manage, because this 5, for instance, over here, it really looks like a 3. Or this one also, come on, this is not an 8. this looks like whatever. So, but then anyway, so there are nice methods. There are a lot of options to do, and depending on the problem you are facing, really see which method applies the most. If the problem is simple, then just go for linear classifiers. If the problem then is really much more complex, you require much more features and information, you can aim for convolutional neural networks. So try then to find the right balance to find suitable solutions, yet not to make the decision making too much complex. Because then if you want to adapt it over time, then it gets also more complicated. Some final remarks. So possible pitfalls of the intelligent system is judging based purely on data than knowledge. Here, this is I've been doing this presentation telling you over and over again on the need of connection between the data and the actual physical system. So if you see a problem from the data, the problem must be in the physical system. Otherwise, infrastructure managers won't believe you anymore. So this the connection with the real problem, then it has to be there very strongly addressed whenever developing solutions in this field. Then this, you don't want to jump to wrong conclusions, because we're talking about a safety critical infrastructure. So if you miss a defect, then it can lead into a disaster. Then also avoid the underestimation of the know-how, and then be careful with causality, of course. In infrastructures and railways, there are many of them that are one of a kind. This is typically the case for bridges, but also in the Netherlands we have different soils, we have different structures, different conditions, that they are sort of one of a kind system, yet there's knowledge that can be used from experiences from other railways that can always help in your own railway system. So although this is always a challenge, because the solutions you provide, they have to be tailored to a specific location, there are still knowledge that we can share and learn from the other infra managers. the challenges addressing here, they have to do with degradation, and it comes from the usage, from the loading, but also by corrosion, cracking, the temperature changes, vibration induced, so many variables. So we are really dealing with a complex system, and we are tackling one specific problem. We have to be aware that there are many other variables that might be influencing our results. So finally, then with the new neural networks, then we can get some more features, general features, then they really help into decision making. There's a problem that we tend to work with a high amount of data, yet there are cases, the black swan, for instance, that are events that are very rare, but they could be very damaging. For them, we also need methodologies where we don't have enough data, but we have the knowledge, physical knowledge. We have also examples that then they can be trained into digital modeling, and then they can provide us some more knowledge about how to deal with them. So, well, I hope then you like the presentation. In case then you're interested in railways, we developed a MOOC that is available, and this one is free for all of you to join whenever it's available. Then it's you don't need to pay for a registration. And then here, this is then it's for the community to get railway knowledge, and it's totally free for you to attend. And and I would like to thank you very much for your attention.
Thanks, Alfredo. Thanks a lot for your lecture. It was a great moment. So I will research for the questions. I will start with one question from Professor Rodrigo Balois. He's our main chair from the events. His question is, how can a young student to prepare for a master program, doctor program in another country, for example, Netherlands?
Well, the depends on the direction, of course. In the Netherlands, we have master programs that they are in English. So there's a tendency to think that all in USA or UK, we can have such education where the language is not a barrier, but actually in the Netherlands, the master programs are in English. There are few bachelor programs that now are still in Dutch, but actually the students are most than welcome to apply and to come to the Netherlands for their master or their PhD programs. And here, most Dutch people speak English, and it's never a problem here, the language. To get prepared, then is the trigger in the motivation of them to go for it, because the teaching systems sometimes are different. You have to adapt to the new conditions, the new kind of teaching courses. But what I have seen from the colleagues, from the students coming from Brazil, they're always so well prepared, they're so reliable, they are really good students. So then I would really recommend you all, then and your students, if you have the chance to come to Netherlands, please do it. Then here the TU Delft, it's a strong university. In some fields, then we ranked even first in the world. So we would love to have more students from Brazil.
Okay, thanks. I hope our students can go to Netherlands.
And such a beautiful country. You saw the videos, and you can bike, and it's a very good quality of life that you get here.
Okay, great, my friend. I have another question. You have different sources of monitoring. What kind of strategies do you use to aggregate all the information?
Oof, that's an excellent question. Indeed, when collecting the information and you are doing it that even in the same round of measurements, there's a tendency of have different acquisition systems. So the first challenge is to actually merge the systems So to know that the information is coming from the first place, from the same place. Then that also holds when measuring at different moments, different weeks. We need to match first that the locations are exactly what we want. For that step, then we use the physical knowledge, information from the past, trend analysis. But then when wanting to merge things together into decision making, we have been using two approaches. One is a sensor fusion approach. So from where you know the value of the information from each of the sensing systems, and we try to get out of it a final conclusion. And the other methodology is to directly include the information already pre-processed, of course, into the learning mechanisms. Because nowadays with the neural networks, you can have vibration signals, images, all of them together into the same structure. So basically, I would say there are those three different steps to consider, two different approaches. And I recently saw a very interesting paper on vibration and images. We did that also many years ago. And indeed, because you see that the patterns on the frequency components, they share some characteristics that it's very suitable also for image kind of processing. So yeah, there are many options, and it's actually one of the most difficult challenges that we face in railways, to really match what we are looking at. The sensor fusion basically is the key.
Okay, my friend, I have another question. In a real scenario, the use of convolutional neural network is more reliable than support vector machines on nearest neighbors in terms of computational costs or the need of real-time response?
For this question, it has really first to do about your needs. If you gotta get a processing that is within few seconds, you definitely prefer a more simplified approach, like the SVMs, that you get some equations and then you can implement it very quick. The thing is that in railways, we have a requirement of for some problems to be online, while for others that are of slow dynamics, that we can wait 1 week, we can wait 1 day. For those cases, then really the computational power is not a problem. Then we can let the multiple computers run in parallel, process all pieces of data that we collect, and we can get a report within a few days. But there are other challenges where we really have to, if there's a broken rail, we have to say right now, right ahead, look, there's a problem here, we have to stop things and to get it better. In those cases, indeed, the current complexity of the networks, once trained, then the time that they consume is the evaluation. But then if you need really, like in the level crossings, for instance, the reaction times are a few seconds. Then it's still the neural networks don't manage to do that. We need responses that are in a very short time. So for them, then definitely what the best you can do is a more simplified approach. So yeah, it really has to do with the problem itself. And indeed, it's not just about the accuracy you want, but also the possibilities and the constraints.
Okay, my friend, we have another question. In oil extraction, which use ultrasound to travel the ground in search of the product, do you use this technique or any other sound technique to understand the conditions of the tracks?
Yes, we do. We use ultrasound to detect the cracks in the rail, but we are also using the radar penetration technologies to analyze the soil conditions. That is because the Netherlands, I don't know if you know, but we are some parts of this country is under the level of the sea. If it were not for the huge dikes that they built, we will be underwater. And actually the TU Delphi, it's at some meters below the sea. So we have really an issue with the ground, and the technologies, the radar penetration and ultrasound, those are all standards for the railways. So we see that at least in Europe, the infra managers are collecting a lot of that information. What we have observed from the analysis we do is that there's still a lot to improve in those technologies. The information that we receive is a bit aggregated. So for instance, with the vibration signals that we get, we can really go into a level of centimeters, even lower. But with the ultrasound or with the eddy current technologies, we get some more aggregated behavior. Then we cannot say like, oh, there's a particular defect here. It's still not possible. But indeed, we have also some projects going on with the laser double emitter, where we also measure vibration without contact. That's we mount a laser, and that one detects how much the rate is vibrating, and then we analyze the responses. So there are plenty of measurement systems being applied, yet the usability or how to improve them with the latest technology, maybe the railways is being a bit conservative about it. So there's plenty of chances also for research when thinking about that sort of technology.
Okay, thanks. We have another question. The intelligent railway is essentially distributed, and one challenge is to assess its condition. Could you give an overview of the challenges to data integrating the railway system?
Yeah, indeed. It's a distributed parameter system because the behavior changes per location, but also over time. So you have also another dimension. You have the different places, similar infrastructure, different behavior. You have the two similar infrastructures, different time, different behavior. So indeed, a challenge that we face here in the Netherlands has to do also with the organization of the railways. We divided the country into maintenance areas where different contractors are taking care of it. And we have an issue about the share of information because we're using the data sets that they get aligned into this information system, that is the official one, from where there's an amount of information shared to everybody, but we have also that the contractors, they might get more information about particular problems, and those are not shared. So I think one of the latest developments in the Dutch railways is about the trust, which is something that, of course, also for intelligence system, we also want trustable methodologies, but then also the trustable organization. So where we can really learn from each other. Although those are companies, they want to get the know-how, a price, and to get the money from it, of course. So it's an economic value, of course, that know-how that they have to protect. Yet there are information that it would be great if it can be shared. So in terms of the integrating of systems, there's experience in the aerospace industry, the oil industry, that they are much more advanced than the railways. Also the highway systems, they have a very much more robust management system. So I would say in terms of the data itself, then it's similar to all those infrastructures. And I would say the challenge is that railways so far was a conservative industry, like, let's say, staying a bit behind of current developments, but it's been drastically changing in the last year. I think then we went back to be then in the top of developments in terms of intelligence systems and technology again. And actually, this year was declared the year of railways for Europe. That's because railways is crucial for the economy, crucial for our societies.
Okay, my friends, we still have a lot of questions, but I think that this is an opportunity for you answer them in the next event, probably next year. And I hope that you'll be here in Piauí, Brazil.
Yeah, looking forward. I would love that.
Probably in Parnaíba, the most beautiful city of the world. It's where it's located, our beach, Parnaíba. or maybe in Teresina, our state capital, or maybe in Picos, the honey capital.
Wonderful.
They are three beautiful cities, and I hope that you came here.
Yeah, when we started our friendship, then Ricardo, then immediately I checked the city and I fell in love with it. I would love that it will happen soon. And for the colleagues or the participants that are having still questions, maybe you can post them in the YouTube channel, and then after I will take the time to answer them, if that is okay for you.
Okay, my friend, okay. So I would like to acknowledge for your participation. It was so gentle, and I will give you the word if you can say anything to the participants.
I hope that you enjoyed the conference, all the workshops, and the interesting presentations. I quick went through the YouTube channel then the other day checking, and it's a very good level. It's a very interesting field. So I hope that you keep motivated, and there's so much contributions that they can be done in so many different fields. And I'm very happy for your invitation, Ricardo, to be here.
Okay. Thanks again, and I will continue with the programming of the event.
Fantastic.
Thanks. Bem, pessoal, gostaria de convidá-los, né, a continuar participando do nosso evento. Ainda temos mais 2 dias de evento, com minicursos, mostras de computação aplicada, enfim, uma série de outros eventos. Agradecer a participação de todos aqui no chat e agradecer a confiança da organização do evento e nos convidar para mediar. Então, desejar aí um excelente segundo dia de evento e espero vê-los mais tarde na mostra de computação aplicada à saúde. Até mais tarde, pessoal.
Muito obrigado.
Muito obrigado, Alfredo. Bye.
Bye-bye.